Hello everyone and welcome to our module on ventilation and perfusion. Ventilation is the movement of air in and out of the lungs, and we can actually calculate a number for ventilation if we know the volume of air going in and out of the lungs and the frequency at which breaths are being taken, meaning the respiratory rate. So for example, if a person were breathing 500 cc's of air per breath and 20 breaths per minute, their ventilation rate would be 10,000 cc's per minute. And ventilation can go to two places. It can go to the alveoli. This is called alveolar ventilation, and this is useful for gas exchange. This type of ventilation removes carbon dioxide and delivers oxygen to the blood. But some ventilation gets wasted, and this is called dead space ventilation. Not all the air that we breathe in and out is used for gas exchange. So a very important concept in pulmonary physiology is dead space ventilation. Let's talk about that now. Dead space refers to portions of the respiratory system that are ventilated, meaning they're filled with air, but they do not exchange gas. Some dead space is simply due to anatomy. This is called anatomic dead space. These are conducting portions of the respiratory tract. For example, your nose and your trachea are very important for the respiratory system to work, but they don't contain alveoli, therefore they are considered dead space. But anatomic dead space is not the only source of dead space. There are also alveoli that don't exchange gas. These are functional dead space, meaning they should exchange gas, but they don't because of the way the system is set up. So we refer to physiologic dead space as the total dead space in the lungs. It's the anatomic dead space, like from the nose and trachea, plus alveoli that don't exchange gas. One of the main reasons for physiologic dead space being greater than anatomic dead space is that there's insufficient perfusion to parts of the lungs. The apex is the largest contributor, and we're going to talk more about this later in this video. But the bottom line is that we have parts of the lungs which have alveoli but don't exchange gas like they should, and they add to our dead space. And as we'll also talk about later in this video, the physiologic dead space increases in many diseases. Obviously, you're not going to increase the volume of your nose or your trachea in disease, but you could increase the number of alveoli that don't exchange gas, and that will increase your physiologic dead space. There is a way that we can measure the physiologic dead space, and that's by using what's known as Bohr's method. Bohr's method says we can determine the physiologic dead space volume Vd if we know three parameters that are fairly simple to obtain. The first one is the tidal volume Vt, the second one is the concentration of carbon dioxide in exhaled air, and the third one is the concentration of carbon dioxide in the arterial system, which we can get from a blood gas. So if we know these three parameters, then we can use this equation to determine the dead space volume. And this equation says the ratio of dead space volume to tidal volume is equal to the arterial CO2 concentration minus the exhaled CO2 concentration divided by the arterial CO2 concentration. Let me pause here and review a little nomenclature on how we refer to the concentration of gases in pulmonary physiology. When we use P with a capital A, we're referring to the alveolar partial pressure. So for example, P capital AO2 is the alveolar O2 concentration. P capital A CO2 is the alveolar CO2 concentration. When we use P with a lowercase a, we're talking about the arterial partial pressure. So P little AO2 is the arterial oxygen content. P little a CO2 is the arterial CO2 content. And then sometimes we talk about other partial pressures like P with a V is the venous pressure, or P with an E is the expired pressure. But usually P is shown with either a capital A or a lowercase a, and that is to distinguish alveolar from arterial concentration. So in order to understand Bohr's equation and what it means, let's go through this drawing I've shown on the slide here. What I've drawn is a working alveolus and a pulmonary capillary. Blood enters the pulmonary capillary with a CO2 concentration similar to what's in the venous system of the body, so I've called that PvCO2. Blood goes through the pulmonary capillary and then it leaves, it goes into the pulmonary veins, the left atrium, the left ventricle, but eventually it makes its way to the arteries, and therefore we can say that the concentration of CO2 in the blood leaving the pulmonary capillary is equal to the arterial CO2 concentration PaCO2. Now, assuming this alveolus is working, as blood flows through the pulmonary capillary, carbon dioxide will leave and enter the alveolus, and by the time that blood reaches the exit of the pulmonary capillary, equilibrium will have been established so that the alveolar CO2 is equal to the arterial CO2. And then finally, up at the top, I've shown that we are inspiring air, which essentially has no carbon dioxide, so the CO2 concentration in the inspired air is 0. Now, to make the picture even more complete, let's give some numbers to the CO2 concentrations. The normal PaCO2 from an arterial blood gas is 40, so let's say that we have a CO2 concentration of 40 here. Blood from the venous system of the body has a higher concentration of CO2 because it's picked up carbon dioxide from tissues, so let's make the CO2 concentration over here 46. And since equilibrium is established between the alveolus and the arterial system, then the alveolar PaCO2 should also be 40. Now, if the only thing we had in our lungs was working alveoli, then all of the expired CO2 gas would come from an alveolus, and therefore the expired concentration of CO2 would be 40. In other words, everything we blow out would come from an alveolus, and it would have the same concentration here that we have in the alveolus. But that never happens because even among healthy subjects, there is dead space. Dead space is like a separate pocket within the lungs that fills with air that is similar to expired air. It has a concentration of 0 for CO2, and then it leaves the lungs and mixes with the alveolar air. What this is going to do is dilute the expired CO2. So instead of being 40, like it would be in a perfect system with 100% working alveoli, the expired CO2 in normal people will be something lower, like 30 or 20, and that's because we all have dead space. Even normal healthy subjects have some dead space. But the main point here that I want to emphasize is if we had a perfect system only with working alveoli, our expired concentration of CO2 would be equal to the alveolar concentration of CO2, which is in equilibrium and therefore equal with the arterial CO2 concentration. So now I've cleared away my ink, and once again let's imagine that the venous CO2 concentration is 46. And now let's imagine that our lungs are made up of no working alveoli. The lungs are entirely made up of dead space. Well, if this happened, carbon dioxide would be 0 in the inspired air, and there'd be no gas exchange because our lungs are all dead space, so the expired carbon dioxide would be 0. So that's what would happen in the worst case scenario. You would expire air with no CO2 in it if you had lungs made up entirely of dead space. And if you're not expiring any CO2, what's going to happen to CO2 in the blood? It's going to build up. In other words, our arterial CO2 will be 46 because it won't have given up any carbon dioxide, and then it'll go around again and it'll get higher and higher and higher. So the more dead space you have, the higher your CO2 will get, and the closer your expired CO2 will get to 0. It's a very important principle of pulmonary physiology. It's the basis of lots of step 1 questions about what happens to expired CO2 as the amount of dead space goes up. So back to the Bohr equation, which is shown on this slide, and now let's talk about what this equation says would happen if we set the dead space to 0 or if we set the dead space to 100% of the total volume in the lungs. So if we had 0 dead space, then this entire left side of the Bohr equation would be 0. We can set that to 0, we can cancel the denominator, and then we find that if we solve this equation, the expired concentration of carbon dioxide is equal to the arterial concentration of carbon dioxide. This is exactly what I showed you pictorially on that last slide. And the bottom line, and the point you want to remember for step 1, is that as we decrease the amount of dead space and get closer to 0, the expired carbon dioxide concentration approaches the arterial concentration of carbon dioxide. That's because more gas is being exchanged and we're retaining less CO2. The less dead space you have, the better it is for gas exchange, meaning the better it is for removing CO2 from the body. If we had 100% dead space, then the entire left side of the equation would be 1. We can set this to 1 and we can solve the equation, and we find out that the expired concentration of carbon dioxide is 0, exactly what I showed you 2 slides ago when we looked at that drawing. So the important principle here is that as the amount of dead space goes up and gets closer to 100%, the expired concentration of carbon dioxide approaches 0. That's because there's less gas exchange. Dead space is bad for gas exchange, and there's going to be more retained carbon dioxide in the body. The more dead space you have, the higher the carbon dioxide will become unless you can increase your ventilation rate to blow it off. So I've been talking a lot about dead space and carbon dioxide, but what about dead space and oxygen? To understand that, let's look at this diagram I've made on the screen. I've shown 2 working alveoli. One is on the left, one is on the right. They are both perfused by a pulmonary capillary. Blood enters the pulmonary capillaries at an oxygen saturation of 70%. This is what typical venous blood oxygen saturation is. After the blood passes through the alveoli, it is fully saturated at 100% on both sides, and then the blood mixes to form arterial blood that is 100% saturated. Now let's imagine we have a disease process that causes flow obstruction to the alveolus on the left. This is going to turn this alveolus into dead space because it is ventilated but no longer perfused. Blood will try to enter this alveolus at 70% oxygen saturation, but it's not going to leave, so the left alveolus, which is dead space, makes no contribution to the arterial oxygen concentration. The alveolus on the right still works, so blood comes in at 70% saturation, it's fully saturated, and it leaves and goes to the arterial system. So what this means is, despite that we have developed more dead space, our oxygen saturation remains at 100% with no hypoxemia. And that's a very important point about dead space. Dead space in and of itself should not cause hypoxemia. There are some diseases with dead space that also have other pulmonary problems that lead to hypoxemia, but the dead space itself should not cause hypoxemia for the reasons we've shown in this picture on the slide. The main problem with dead space is that this alveolus on the left is not picking up any carbon dioxide. The carbon dioxide content there is going to be 0. This is going to leave and mix with carbon dioxide from the working alveoli. That's going to decrease the PeCO2 that we talked about before. And because we have parts of the lung now that are not picking up carbon dioxide, that can potentially lead to elevated carbon dioxide in the blood, which is hypercapnia. And that brings me to a huge point about dead space. The main problem is that it raises the CO2 concentration in the body. This can potentially lead to hypercapnia. It often doesn't because patients increase their respiratory rate. In other words, they ventilate these healthy alveoli more to compensate for the ones that aren't working, that are dead space. And we'll talk more about this in a minute. But the big point that I want to make here is that the main problem with dead space is not hypoxemia. It's that the CO2 level can go up, leading to hypercapnia, unless patients can increase their respiratory rate. Now we're going to move on from dead space and talk about the alveolar ventilation equation. This is one of the classic equations of pulmonary physiology. It's used to predict the alveolar carbon dioxide level. So to understand this equation, we first have to understand total ventilation. So total ventilation to the lungs is a volume per minute of air that moves in and out of the lungs. It's sometimes also called minute ventilation. And this is sort of a minor detail, but the volume that we take in is slightly greater than the volume that goes out, and that's because oxygen is taken up from the lungs into the bloodstream. Alveolar ventilation is different from total ventilation. Alveolar ventilation is total ventilation minus the dead space. So for example, if 500 cc's per minute are going in and out of our lungs, but 150 cc's per minute is filling dead space, then our alveolar ventilation is only 350 cc's. That's the ventilation that's available for gas exchange, and that's the ventilation we're going to need to use to predict the alveolar CO2. Now I'll show you the alveolar ventilation equation in a second, but before I do, I want to make a brief side point about elevated carbon dioxide in the blood. This is referred to as hypercapnia or hypercarbia. Both terms mean the same thing. And it's bad because elevated carbon dioxide leads to a respiratory acidosis, which I talk about in videos in the renal section. So because the body doesn't like having high carbon dioxide, it has a physiologic response. Elevated carbon dioxide levels are sensed by the brain, and the body responds with an increase in the respiratory rate, which blows off carbon dioxide. In other words, the alveolar ventilation increases in response to elevated carbon dioxide. And this is a very important principle of pulmonary physiology for you to understand. Disease processes which could raise the CO2 level often do not, because the body responds with a rise in the respiratory rate. Shown on this slide is the alveolar ventilation equation. It says that the partial pressure of carbon dioxide in the alveoli is equal to the rate of carbon dioxide production, that's the VCO2, times a constant K divided by alveolar ventilation. And this equation has so many things in it that can help you answer step 1 questions about pulmonary physiology. What it is saying is that the concentration of CO2 in the alveoli will go up if the body produces more CO2, and that should make sense to you. If the production of CO2 rises, then that can potentially raise the alveolar concentration of CO2. On the other hand, if you increase the alveolar ventilation, that is going to tend to lower the concentration of CO2 in the alveoli. And this should make sense to you. As you ventilate the lungs more, you blow off more CO2, and therefore you lower the alveolar PaCO2. Now, another important point, although the rate of CO2 production, that's the VCO2, can potentially raise the alveolar CO2 concentration, it usually does not. And that's because anytime we begin producing more CO2, our body increases our ventilation rate. And you know this from exercise. When you exercise, your muscles produce more carbon dioxide and your ventilation rate goes up. And for that reason, people who exercise do not develop hypercarbia. They do not develop an elevated CO2 level because the increase in the rate of production of CO2 is being matched by an increase in alveolar ventilation. Now I'm going to slightly modify the alveolar ventilation equation, and instead of writing alveolar ventilation in the denominator, I'm going to write total ventilation minus dead space ventilation. Because remember what I told you on the last slide, alveolar ventilation is total ventilation minus dead space ventilation. If we write it this way, what you can see is that if the dead space volume goes up, that is going to make the denominator smaller, and therefore it's going to raise the PaCO2. And that's consistent with what we were just talking about in the last few slides, that dead space can potentially cause the CO2 concentration to go up. Now, dead space does not always cause the CO2 concentration to go up, and that's because if we're able to increase our total ventilation, we can offset the rise in dead space. So for example, imagine our dead space volume rises by 50 cc's. Imagine then we also increase our total ventilation by 50 cc's. If we do this, then the PaCO2 is not going to change. And that's why when dead space goes up in disease processes, it doesn't always lead to elevated CO2 level. If patients are able to increase their ventilatory rate, they can offset the rise in dead space. So I'm going to summarize this now by writing the three major causes of CO2 increase, all of which are evident from the alveolar ventilation equation. If you understand this, it is super high yield for step one. It can help you to answer many, many questions. So the only way the CO2 level is going to go up is if there's either increased carbon dioxide production, decreased alveolar ventilation, which is hypoventilation, or increased dead space. These are the only three reasons that hypercapnia can develop. Also remember that the one in the middle is the most important. If you can increase your ventilatory rate, you can offset an increase in carbon dioxide production just like we do with exercise. If you can increase your ventilatory rate, you can also offset a rise in dead space, as many patients do with diseases associated with dead space. If you understand this, you're all set for answering questions about hypercapnia on step one. Now let's move on to the alveolar gas equation. And just like the alveolar ventilation equation can be used to predict alveolar carbon dioxide, the alveolar gas equation can be used to predict the alveolar oxygen level. The alveolar gas equation is shown at the bottom of the screen. It says that the alveolar oxygen concentration is equal to the oxygen in the inspired air minus the CO2 content in the alveoli divided by R. R is the respiratory exchange ratio. So let's talk about what this means. First of all, if you inspire more oxygen, in other words, if your PiO2 goes up, that is going to raise your alveolar O2, and that should be fairly obvious. If you inspire gas with more oxygen, it's going to put more gas into your alveoli. And if a person is breathing 21% oxygen, which is normal atmospheric oxygen at sea level, the PiO2 is going to be 150. And this is sort of a handy number to remember here. The PaCO2 is what we've been talking about in the last few slides. It's the alveolar CO2 concentration. And then R is the respiratory exchange ratio. This is the ratio of CO2 produced for every oxygen molecule consumed. And this varies with your diet and metabolic state, but usually the value for R is 0.8. That's what it's usually assumed to be for the average person. So what this alveolar gas equation is saying in the second part here is that although you may inspire a certain amount of oxygen, some of that oxygen is going to be taken up by the body and carbon dioxide is going to be added to the alveoli, and you need to subtract that amount in order to calculate the PaO2. And now I've cleared away my ink so I can make another very important point. What this equation says is that anything that raises your PaCO2 is going to decrease your alveolar oxygenation, and that should make sense to you if you think about it. We have just been talking about how hypoventilation will raise the PaCO2, and hypoventilation is also a classic cause of hypoxemia, and that's because when you don't ventilate the lungs well enough, what you get is a high CO2 level and a low oxygen level, and that's just what this equation is saying mathematically. Any cause of hypercapnia will also cause alveolar oxygen level to fall, and therefore that can lead to hypoxemia. And just to make this even more clear, let's look at this table I've put on the screen. So a normal alveolar PaCO2 is 40, and I told you before that a normal inspired O2 is 150. So if you plug those numbers into the alveolar gas equation, you get a PaO2 of 100, which is a normal level of oxygen in the blood. However, if the PaCO2 becomes 50, then when you plug in the numbers, the PaO2 drops to 88. And if the PaCO2 gets really high, like all the way down here at 80, then what you're going to get for PaO2 is 50. So all I'm showing you in this table is the relationship between carbon dioxide and oxygen. When you hypoventilate, you tend to raise the carbon dioxide level. That's what's happening in this column here. And when you hypoventilate, you tend to decrease your oxygen level, and that's what's happening in the last column. And all of this comes back to the alveolar gas equation shown at the bottom of the slide. So up to this point, I've been talking about ventilation, but what I'm going to do now is switch gears and talk about perfusion of the lungs by blood. So we spend most of our time in the upright position during the day, and when we're in that position, blood flow distribution to the lungs is uneven. This is because of gravity. Because of gravity, the apex, the top of the lungs, has the least blood flow, and the base has the highest blood flow. Basically, you need to generate energy to pump blood all the way up to the apex, and it's harder to do that, so there's less blood flow. It takes less energy to drive blood flow through the base, and therefore there's more blood flow there. And the lungs are classically divided into 3 zones in order to describe perfusion of the lung. So here's a picture of the lung. Zone 3 is the base, that's where the blood flow is the highest. Zone 1 is the apex, that's where blood flow is the lowest, and zone 2 is in the middle. And just like perfusion varies as you go from the bottom to the top of the lung, so too does ventilation. Just like perfusion, ventilation is highest in zone 3, which is down at the bottom of the lung, and it's lowest in zone 1, which is at the apex. Just like perfusion, this is also caused by gravity. The idea here is that at the base of the lung you have air spaces which are compressed by the lung that sits on top of them. In other words, during exhalation, the lung above the air spaces at the bottom pushes down on the air spaces at the bottom and pushes air out. What this means is when the next breath comes in, there's more room for air to enter the lower parts of the lung than the upper parts of the lung. And as a result, there's more ventilation at the base compared to the apex. And I've summarized these points here on this slide. The upper lung compresses the base, pushes air out, and then there's more room for filling of the base with the next breath. And then finally, an important point that you need to understand, and this will come up again in a few slides, is that although ventilation is highest at the base and lowest at the apex, the change in ventilation from the base to the apex is smaller than blood flow. In other words, there's a much greater change in perfusion as you go from the base up to the apex. There's a much smaller change in ventilation as you go from base to the apex. So it's important to understand about ventilation and perfusion and how they change in different parts of the lung, but what really matters in terms of gas exchange is the ventilation to perfusion ratio. This number is the alveolar ventilation in liters per minute divided by the pulmonary blood flow, and matching of ventilation to perfusion is critical for gas exchange. If you have parts of the lung with great ventilation but very little blood flow, that's inefficient for gas exchange. The same is true if you have lots of blood flow but very little ventilation. So the normal VQ ratio, the ventilation to perfusion ratio for the entire lung, is 0.8. And this number comes from simply dividing the alveolar ventilation in liters per minute by the pulmonary blood flow in liters per minute. And this normal VQ ratio is what gives us our normal gas content in the arterial blood of a PaO2 of about 90 and a PaCO2 of about 40. If ventilation and perfusion become off, then these numbers might not be achieved. So just like ventilation and perfusion vary as you go from the base to the apex of the lung, so too does the ventilation to perfusion ratio. Let's talk about the base first. At the base, you have the most blood flow, as we talked about before, and also the most ventilation. But remember what I said earlier, the variation in blood flow is much, much greater from apex to base than the variation in ventilation. What this means is that at the base, we have a lot of blood flow, and we have more ventilation in other parts of the lungs, but not that much more. So this gives us the lowest VQ ratio in the lung. That's what's found at the base. And it's very easy to remember. The lowest value is simply found at the bottom of the lung. And the fact that the VQ ratio is low means we're wasting blood flow. So we've got lots of blood flow here, but we're not ventilating it as well as possible because the ventilation doesn't match the blood flow. At the top of the lung, we have the lowest blood flow and the lowest ventilation, but once again, the decrease in blood flow is much greater than the decrease in ventilation. Therefore, at the apex of the lung, we have the highest VQ ratio. What this means is that we're wasting ventilation, so we have great gas exchange up at the apex, but very little blood is going through there. We're not getting the maximal use out of that ventilation because the amount of blood flow is so small up at the apex. So I've summarized these points here. Both ventilation and perfusion decrease from the bottom to the top, but the blood flow decreases more. As a result, the VQ ratio changes. And once again, it's very easy to remember this: lowest at the bottom, highest at the top. On this table, I've shown all the changes in ventilation and perfusion parameters as you go from the base to the apex of the lung. This chart is the source of many, many questions on step 1. Don't just memorize it, make sure you understand it, because you will see lots of questions that derive from this information. So as we talked about earlier, at the bottom of the lung, the ventilation is the highest and so is the perfusion, and at the top of the lung, the ventilation is the lowest and so is the perfusion. However, at the bottom of the lung, the VQ ratio is very low. It's as low as 0.6 at the bottom of the lung. At the top of the lung, the VQ ratio is very high. It's as high as 3.0. Now, because the VQ ratio is low at the bottom of the lungs, you don't get the most efficient gas exchange. So the PaO2 of blood leaving the base of the lungs is about 90, and the PaCO2 is about 42. And remember that a normal PaO2 is about 90 to 100 or so, and a normal PaCO2 is about 40. So you're getting numbers that aren't quite as good coming out of the base. At the apex of the lung, you get numbers that are fantastic. The PaO2 is 130 and the PaCO2 is all the way down to 30. The problem here is that you don't have much blood flow that's achieving these numbers, but the blood that does get up to the apex gets excellent gas exchange. And then of course the blood from zone 1 and zone 2 and zone 3 all mixes together. It goes to the left atrium, the left ventricle, and into the arteries, and in the arteries you get the PaO2 of 90 to 100 and a PaCO2 of 40. So let me emphasize a couple important points about zone 1, which is the apex of the lung. It has the lowest blood flow and the lowest ventilation, but the highest VQ ratio. And because the VQ ratio is so high, gas exchange is excellent here, and we have the highest PaO2 and the lowest PaCO2. And because the PaO2 is so high in the apex of the lungs, bacteria that like oxygen, like tuberculosis, often develop infection in this portion. This is someone who has a cavitary tuberculosis lesion at the apex of the right lung, and tuberculosis loves to infect this location because of the high VQ ratio and the high PaO2. So earlier we talked about perfusion and how it varies from the base to the apex. I'm going to revisit that topic now and talk a little bit about what drives pulmonary blood flow in different portions of the lung. So if you look at the bottom of the screen, I've shown a pulmonary capillary. We've got blood coming in from the pulmonary artery at the pressure P sub A, and we've got blood leaving and going to the pulmonary veins at a pressure P sub V. And normally it is the difference between PA and PV that drives the blood flow. If PA is significantly higher than PV, you'll have lots of blood flow. If it's not that much higher, you'll have less blood flow. And I've summarized this point on the slide. Normally the AV pressure difference is what drives blood flow. However, in the lungs, you have a third pressure, the alveolar pressure, and this can press down on the capillary, and this can affect blood flow. If the pressure in the alveoli is very high, it can compress the veins or the arteries, and this can lead to no blood flow. And when you have no blood flow but you still have ventilation, that's what we call dead space, which is what we talked about earlier. So let's go through the zones of the lung just like we did before, and we're going to talk about how the alveolar pressure impacts blood flow. So alveolar pressure, P with the big A, is the same all throughout the lungs. What's different is the pressure in the arteries and the veins. So you have the highest pressure in the arteries and the veins down at the base. So let's talk about what that means. So with the highest pressure, the pressure in the artery and the pressure in the veins is always going to be higher than the alveolar pressure. So alveolar pressure has no impact on blood flow down at the base, and that helps to achieve the highest blood flow at the base, which we already know because we talked about this earlier. In zone 2, the mid-zone, the alveolar pressure becomes higher than the venous pressure. Well, here's a pulmonary capillary. This is the venous side over here, and this is the arterial side over here. This venous side is going to be smushed closed by the pressure in the alveoli. What's going to happen though is that pressure on the arterial side goes up and down as the right ventricle contracts. When the pressure on the arterial side is at its highest point, it will be able to push open the venous side and generate some blood flow. So what that means is in zone 2 in the middle of the lung, what you're going to get is pulsatile blood flow. Blood will flow only when pressure on the arterial side is at the highest, and it won't flow when pressure is lower than that on the arterial side. And now let's talk about the apex. At the apex, the pressure in the alveoli is equal to or greater than the pressure in the artery. If it's greater than the pressure in the artery, you're not going to get any flow. The alveolar pressure will completely compress the artery and not allow any blood in. If the pressure is equal, you may get minimal blood flow, and that's what happens at the apex. You get minimal or no blood flow because the pressure in the alveolus is higher than the pressure in the artery. And I've summarized the key points here. The alveolar pressure is constant throughout the lungs. At the base, PA and PV are the highest, and at the apex, PA and PV are at the lowest. Therefore, at the apex, you have the least flow, and at the base, you have the most. Let me make a super high yield point about zone 1. That's the portion of the lung at the apex where the pressure in the alveolus is equal to or greater than the pressure in the arteries and veins. If you have a slight fall in the arterial pressure, that's going to lead to capillary compression, and this can happen in many pathologic conditions like hemorrhage or shock. When this happens, zone 1 is going to become dead space. It's going to be ventilated, but it won't have perfusion. And that's something they like you to know for step 1. A small change in blood pressure to decrease the arterial pressure can lead to zone 1 becoming dead space. Last topic for this video is exercise. So when you exercise, you increase oxygen demand, your ventilation rate goes up, and so does your cardiac output. The VQ ratio for the entire lung is going to approach 1. That's because there's more blood flow and more ventilation, but the increase in ventilation is greater than the increase in blood flow. In addition, the VQ ratio becomes more even in the zones, so there isn't as much change in going from the base to the apex. Let's look at my drawing on the screen. I've got a pulmonary capillary here. Oxygen is coming in and carbon dioxide is going out. With exercise, the oxygen and carbon dioxide content in arterial blood is not going to change. The reason it's not going to change is because your body is increasing the ventilation rate and the perfusion of the lungs so that even though there's more oxygen demand and more carbon dioxide to be excreted, the lungs can handle it. So there's going to be no change in the mean arterial oxygen and carbon dioxide content. On the venous side of the lungs, however, things are going to change a lot. You have much more carbon dioxide produced. So normally the venous carbon dioxide content is about 46. This can get much, much higher than that during exercise because the body's producing so much more carbon dioxide. Also on the venous side, the oxygen content can get as low as 40 under normal circumstances. During exercise, this can get much, much lower because your tissues are consuming more oxygen. So the key point, and once again, this is super high yield for step 1, is that with exercise, if you look at an arterial blood gas, there's not going to be any change in the oxygen and carbon dioxide content. But if you look at the venous blood, you're going to see a huge change. Much less oxygen in the venous blood, much more carbon dioxide in the venous blood. The reason it's not changing on the arterial side is because ventilation and perfusion are increasing so that the lungs can blow off the extra amount of CO2 being produced by exercise, and so that the lungs can replace the extra oxygen being used up during exercise. And that concludes our video on ventilation and perfusion.